Let's continue to look at more examples of application of pigeonholes. This is a good one. Say, let A be the set of numbers from 1 to 8. What is the least number of integers that you have to choose so that the sum of the two of the chosen integer is 9? So you're going to choose integers from this set. How many do you have to choose so that you guarantee that sum of the two of the chosen integer is 9? All right, again, you have to think about how to cleverly design your holes and pigeons. So that's the key part, right? Now, the chosen integer, the sum is 9. So what are the possibilities to get the 9 from these numbers? You can see that 1 plus 8, that can be 9, right? And then 2 plus 7, that will be 9. 3 plus 6, that will be 9. And 4 plus 5, that will be 9. So those are the possible combinations that you get the sum being equal to 9. So actually this becomes my holes. Okay, that's how many holes do I have? This is the first hole, second hole, third hole, the fourth hole. So these are the holes. Those are the pairs. And the pigeons, think about these 8 numbers, 1, 2, 3, 4, 5, 6, 7, 8. These are the pigeons. And when you map, so f of the pigeons are those numbers. So f of the number is equal to, well, say if you choose 2 is chosen, then we'll put the 2 in this hole. 3 will put that into this hole. 8 will put that into this hole. So f of number will be going to the hole or the pair, right? Basically the pair that contains the number. So for instance, if f of 1, then it will go to this hole, 1, 8, this hole. So in this case, your m is equal to 4, right? 4, 1, 2, 3, 4, 4 holes. So what must be, because m is equal to 4. Therefore, how many do you have to choose to guarantee that at least one hole there were two pigeons, right? So n has to be 5 or more. So n has to be greater than or 5. So you have to choose at least 5 integers. Then you guarantee you get at least one pair that add to 9. All right, let's take a look at the next one. How many integers must you pick so that at least 2 of them have the same remainder when divided by 7? Okay, so again, think about it. What would be your whole? What would be your pigeon? So how many integers you must choose? So now, pigeons. So let's just say all the integers that you're going to choose. That's the pigeons. And what are the holes? Because we're divided by 7. If you look at the remainder, there are 0, 1, 2, 3, 4, 5, 6. Those are possible remainders, right? When you divide it by 7. So those are the holes. In other words, m is equal to 7. And what is the mapping? F. So f of any integer, say let's just say f of I represents the integer that you are being chosen, will be equal to the remainder of I when divided by 7, right? So when divided by 7. So in this case, m is 7, therefore, so because m is equal to 7, therefore you have to choose 8 or more. Once you choose 8, it guarantees that at least 2 of them have the same remainder, okay, when divided by 7. So this is it. Now let's take a look at a couple more examples. These are interesting examples. The first one is the decimal expansion of any rational number either terminates or repeats, So rational number means fraction of the two integers, right? So for instance, like 7 over 5, that terminates, that's 1.4. Or if you have, say, 1/3, that's 0.33, never ending, but it repeats. Or if you say, yes, so that's those are some examples. So it's either terminates or repeats. How do we prove that? Say, let's take a look at, let's use one example to understand the idea. So I'm going to say, suppose we look at this, 3 over 14, right? 3 over 14. So let's find its decimal expansion. So we are going to do a little long division, 3 over 14. So 3 doesn't go into 3, so we have to introduce a decimal and then get the 0 here. So 30 divided by 14. 30 divided by 14, 14 goes into 30 twice. That's 28. We subtract, you're left with 2. Okay, and now this 2 is the remainder when 30 is divided by 14. Now to continue the division, we have to add the 0, and let's see how many times 14 goes into 20. It's just 1 time. So therefore 14, and we subtract 6, and then we have to get a 0 again. And 14 goes into 60. How many times? It will be 4 times. 4 will be 56. So when we subtract, this is 4, and then get another 0. 40 divided by 4. How many times 14 goes into there? I think it won't be 3. It's gonna be 2. 2 will be 28. Then we have 12. Okay. Now we are gonna continue. Seems like we are running out of space. Let's get a little extra space. So 14 goes into 128 times. So 112, and when we subtract, this is 80. So 14 goes into 85 times. 5 times, that will give us 70. And then when you subtract 10, and then add another 0, 100. Now 100 divided by 14, this is going to be 7 times. You get 98. Okay. Now when you do that, 2. Now once you see the 2, that repeats, right? That repeats. If you continue the 0, 20, then that will be 20. It will repeat. So therefore, this whole thing will repeat. From this point on, it will repeat. So once you see the repetition, this portion will repeat. Now let's actually prove that the decimal expansion of any rational number either terminates or repeats. Okay, so let's say, consider, here's the proof, consider A divided by B. Let's for convenience purpose, let's assume A is less than B. So this is less than B. So assume A is less than B with A less than B, and we also assume they're both 0, both positive. Now, how do we apply the pigeonhole principle? So let's think about what would be your holes, what would be your pigeons, right? So the holes, actually, that would be the holes. Like when we see the repetition, that will repeat. So we are going to think about holes being the remainders. So think about holes being the remainders. And of course, because we are dividing by a number, so therefore it's pretty obvious that we have finitely many holes, right? It's not infinite, so we have finitely many holes. Okay. Now, say let the remainder, let R0 be A, the first number. Let first number be A. That's my 0th remainder. That's where we begin with. And let R1, R2, and so on and so forth. Okay, we don't know how many, but it should be finitely many. So let R1, R2 continue. I'm sorry, not finitely many. If you want to, you can continue indefinitely. This process, if you want to, you can continue indefinitely. So there were a whole bunch of remainders. There were infinitely many remainders if you want to continue, but they will repeat. That's the whole point. So let R1, R2, R3, and so on and so forth be the successive remainders when you divide it. So remainders from the division, when you do this from the division. And by the way, these remainders, they must be from 0 to b minus 1, right? Just like here, when you divide it by 14, the remainders cannot be, it needs to be either 0 to 1 up to 13. It won't be 14, so it will be from 0 to b minus 1. Those are the remainders. So those are the holes, right? Those are the pigeonholes. Now, of course, if at some point Ri is equal to 0 for some I, so one of those becomes 0, then that definitely terminates. We divide that, the remainder is 0, then it stops, right? Then it terminates. The division terminates. So that's this case. Now, if none of those is equal to 0, if Ri, none of those is equal to 0 for all I, then the division never ends, right? Never ends. So never ends. We want to prove that it will repeat. Now, think about the R1, R2, R3, and so on and so forth. And those are the pigeons. And here the holes will be from 0, 1, all the way up to b minus 1. We know this is finite because b is a finite number. And f is a map that maps this remainder to one of those, right? To one of those. So because m is equal to, there are b number of holes from 0 to b minus 1. And there are many remainders, right? So n is equal to infinitely many. Okay. So by this, so with that visualization by pigeonholes principle, and we have, some of those must repeat. Some of those must repeat. That's for sure, because we have more pigeons than holes. So by the pigeonhole principle, some Ri must be equal to Rj for some R and J, right? I and J. For some I and J. Where say suppose I less than J, okay? I less than J. So therefore, so from Ri plus 1 all the way up to J minus 1, because Ri the same as Rj, like these will certainly repeat, right? Those are the ones that will repeat. So that's one. Then we prove this case. If it doesn't terminate, then it must repeat. Okay, so this is a pretty neat application of the pigeonhole principle. Now let's finish this section by looking at the very last example, also a very neat application. Say you randomly put 5 points in the interior of a unit square. So you have a unit square here. Okay, length is 1. Length is just 1. And you're going to put 5 points. Show that at least 2 points are within this distance, square root of 2 over 2. Square root of 2 over 2. Now, again, think about how you would approach this problem and how you would assign pigeons and holes. Now, the holes, I'm going to say that this is the square, okay? And we're going to divide that into four regions, 4 little squares, 4 quarters. And let's call this as hole number 1, hole number 2, hole number 3, hole number 4. And by the way, if you look at the distance, right? In each hole, what's the distance? What's the max distance? This will be the max distance in each hole. And because this is going to be a half, this is going to be a half, this will be square root of 2 over 2. So this is the max distance. Now, if you have, so these are my pigeonholes. So I have 5 points, say point 1, point 2, point 3, point 4, point 5. These are the pigeons. And then, F will be just you can place them in any way you want. Just place into one of those holes, right? So please note that each hole, the max distance is less than square root of 2 over 2. Because we want to put that interior. You don't want to think about the extreme scenario like on the boundary. In this case, that will be equal to square root of 2 over 2, not within, right? But now if you put this in interior, so this point is inside, okay, not on the boundary, then we can guarantee that the max distance is strictly less than square root of 2 over 2. Now, because we have 4 holes and here we have 5 pigeons, therefore we can conclude that at least, because n is 5, m is 4, right? So therefore we can conclude at least one hole must have 2 pigeons, which is the points. So therefore the distance must at least 2 points. That with the distance must be within square root of 2 over 2.